Hello students, my name is Shashank Shekhar. So we are doing the chapter that is electrochemistry and today is our 7th day. So yesterday we have completed the second part of this electrochemistry and today we will be seeing the remaining portion. So the chapter is electrochemistry and this is our syllabus that we have. So we have seen up till this part. So if you want a reminder, I will just tell you in 2 or 3 minutes. So the first part was mainly about our EMF calculation, in which we have seen our Nernst equation. The equations are like this: E cell is equals to E naught cell minus RT by NF ln Q. So this was our Nernst equation. Then we have seen the relation between our Gibbs free energy and our EMF of the cell. So this was our first part. In the second part, what we have seen different kind of quantities which can measure the current. So we have seen resistance, and then we have seen conductance, specific resistance, specific conductance, in which specific conductance is also termed as resistivity, and conductivity, and specific resistance is also termed as resistivity, right? So this was our thing. So if you remember the formulas of all of this. So we have this conductance, which is equals to 1 by R, or reciprocal of resistance. Then we have resistance, which was equals to R is equals to rho L by A, where rho is our specific resistance. If you just take the inverse of this, it will be 1 by R, 1 by rho, A by L. Of course, it will be capital A by L. Okay, so 1 by R is this conductance and 1 by rho is termed as specific conductance or conductivity, which was represented by kappa. Then it is multiplied by, now representing it with the A, small a, yes. Again, we have some more say terms which were molar conductance, lambda m, and equivalent conductance, which can be represented by this or simply this lambda. So it was due to 1 gram equivalent. So it is the conductivity which is offered by the species which is present in 1 gram equivalent of that electrolyte. Again, we have this molar conductance. So this molar conductance is basically the conductivity that is offered by the ions present in 1 mole or 1 molar concentration of that substance. So this was our thing. If you consider the formulas, it is simply K into phi, where phi is the volume containing 1 gram equivalent of the substance, and lambda m was kappa. So kappa, not K, it is kappa. Kappa into 1 by C, where C is the concentration, or you can say molarity. 1 by molarity. So these were our terms in the previous class, and then we have seen laws which are defining the variation of these different quantities along with concentration. The first one was, say, lambda is equals to lambda naught minus A root C. This was for strong electrolytes. Strong electrolytes. For weak electrolytes, we have this Ostwald dilution law. Weak electrolytes, we have this Ostwald dilution law. So it was basically alpha is equals to lambda by lambda naught. Now this is more appropriate if we write here lambda m, or it can be lambda equivalent also, so both will be equal. So what is this lambda naught m first of all? So this is the molar conductivity at infinite dilution. What it is? It is the molar conductivity at infinite dilution. Means suppose we are taking a very small amount of this electrolyte and dissolving it in a large amount of aqueous solution. Then in that case, the conductivity is termed as our molar conductivity at infinite dilution. So if you consider the graph, it looks like this. For strong electrolyte, it was going from here to here. And for weak electrolytes, it was something like this. Okay, it was something like this. So this is, you extrapolate it, you will get this as lambda naught. So just compare this thing with y is equals to mx plus c, where m is minus a and it is a negative slope. K is concentration, root c. So we are plotting graph root c against our lambda m. So this was our laws for this strong and weak electrolytes. Further, we move to a Kohlraas law. So what does this law suggest? So suppose we have electrolytes that is like our NaCl. Then at infinite dilution, so this law was proposed for that solution only which have infinite dilution. So if we can write lambda naught NaCl like this, lambda naught Na plus and Cl minus, where these are the individual contribution of our cation and anion. Again, we can have H2SO4. So the thing here to notice is that either we will write 2 lambda naught H plus. Why? Because H or hydrogen has 2 kind of equivalence in this H2SO4, and for SO4 we have this SO4 2 minus. So here is 1 present, here is also 1 present here, but since we can write it, we should not write it as it is understood by writing it this way only. Okay, so this is our Kohlraas law. So if I want to make the statement, it is that it is written that the molar conductivity of any electrolyte at infinite dilution is equals to their individual contribution from cation and anion. Okay, so this is our Kohlraas law. So up till this we have seen, so 2 parts. First of all, the conductivity, molar conductivity and Kohlraas law, and this all things, they make up the one part, and the second part is our Nernst equation and relation with our Gibbs free energy. Now moving on to the today's class. So if you see here, so we are done up till this. So today we will mainly deal with electrolysis. So what is electrolysis? First we will see what is electrolysis, and we have law of electrolysis. So it was given by Faraday. So we'll just see some elementary ideas in this. So we'll see those laws. So to begin with today's class, the topics which we'll be covering today will be what is electrolysis, and we will see some applications. So in industry, this electrolysis find a very wide approach, or you can say very wide use, because electroplating and all these things are based upon this electrolysis only. So we will see this, what is electroplating and what is purification and all, how does this electrolysis contribute in all these industrial processes. Next, we will see Faraday's law. So it has 2 laws, Faraday's first law and Faraday's second law. We will see their formulations, that how the formula is formed, and at last we will see some illustration so that we can get a more clear picture of this Faraday's law. Starting with our electrolysis. So I want to make a point is that this electrolysis has been taught in the previous class also. So it had been taught in the previous class. So you must have seen this diagram in NCERT in class 9th or 12th, I think. 9th or 10th, I think. So this diagram, you must have seen this, and you have must have heard this term also, electrolysis. So I'm just again repeating this thing. but in a more, you can say, conceptual manner. We will go to the technicalities also. So we have studied electrochemical cells. Those are of two types. The first was of galvanic cell. So if you remember what is galvanic cell, it was basically conversion of your chemical energy into electrical energy, or gives energy, free energy of a spontaneous redox reaction into electrical energy. So that was our galvanic cell. But electrolysis is just the reverse of it. So what do? Is we use electric current to drive a non-spontaneous reaction, or redox reaction more appropriately. So what we are doing is we are connecting the setup as usual, just like our, say, this galvanic cell, but some changes we have made here. So you can see that we have used only one compartment, but all other things are same. So it depends upon our means what kind of reaction we want, what kind of results we want. In keeping these things in mind, we prepare our setup, but the basic concept remains same, that we have a electrode dipped in their electrolytic solution and connected through wire. So this is common. So the principles remain same. Now initially we are conducting the reaction, and the resulting current was the this output of this reaction. But now what we are doing is we are applying voltage with the help of a cell. So you can see here it is a cell representation, which is like this, where this longer one denotes the positive potential and the shorter one denotes the negative potential. So in electrolytic cell, an external cell voltage is applied to bring about a chemical reaction. So the same thing is mentioned here also. So one of the simplest electrolytic cell consists of two copper strips dipping in an aqueous solution of copper sulfate. So this is our example. So we have taken a copper sulfate solution. So this is our copper sulfate solution. It is written here also, acidified copper sulfate solution. And we have dipped two copper strips here. So this is the first copper strip, this is the second copper strip. And we are doing this thing for purifying our copper metal. So how it is happening? See, you can see here that we have this unpurified copper metal. So we have impurities along with this electrode, and this is our purified one. Now as we will turn on the key, so this is having a positive potential, due to which it will attract electrons. Okay, so it will attract electrons. So this thing will release electrons in this way, and will release Cu2 plus ion in the solution. Okay, now this negative charge will go here, it will flow like this and go on this electrode. Now this electrode is negatively charged, so it will attract this Cu2 plus ion, which was released by this unfiltered copper. Now this Cu2 plus will move toward this cathode and will be accumulating upon this electrode. Now during this process, the impurities cannot move, because most of the impurities will consist of this carbon and all, and you know that they are not much polar. They are not polar at all, I think, in comparison to this Cu2 plus and all these ions. Not due to this reason, they will just precipitate, or you can say not precipitate, they will be forming layer in the downward area. So here is our impurity, that is the anode mode, because it is coming from anode, so it is termed as anode mode. And this copper, pure copper, is gaining the electron that was released by this electrode, and making here is the making of pure copper from impure copper using electrolysis. So the same thing is mentioned here. So one of the simplest electrolytic cell consists of two copper strips dipping in an aqueous solution of copper sulfate. Now if a DC voltage is applied to the two electrodes, then copper is converted to Cu2 plus. Yes, this copper is converted to Cu2 plus. Ion at the anode by the reaction. The reaction is this, where Cus is going to Cu aqueous, and it is releasing two electrons. Now at the same time, on the cathode we have this copper metal deposition. So basically the electron that was supplied by our anode is received by the cathode, and since we have copper 2 plus ions which was released by this anode, so this will be taken up by the two electrons and will form Cu solid. and also we are collecting the impurities in the tank here. Now what we have done in a nutshell, we have just made, or you can say purified, copper using our electrolysis, in which we are taking both the electrodes as copper. So one is getting oxidized and one is getting reduced, and we are taking a copper sulfate solution. Is it clear? Right. Now if I talk about the applications and all, so we have many applications, starting from our impure copper into copper of high quality, which we have seen right now in the previous lecture, or in the previous slide, sorry. So we have converted this impure copper into our high purity copper. Again, we have some more application of this, like the sodium and magnesium metals are produced by the electrolysis of fused electrolytes. What is the meaning of this? So we are taking this sodium and magnesium salt, so they are basically present as chlorides, and we are again doing the electrolysis like the previous one, and we are getting our sodium and magnesium metal pure form. Similarly, aluminium is obtained by the electrolysis of aluminium oxide in the presence of cryolite. So here is our Al2O3, that is aluminium oxide, and we are taking it in the molten state and we are applying potential, and at the bottom we are getting our molten aluminium. This is a pure aluminium. So in this way we can use this electrolysis in getting our pure form of any metal. So these are pure form. Now one more use which is not mentioned here, sorry for not including this thing, so it is also an important application of this electrolysis, which is electroplating. So what do? We take the same compartment as the earlier one. The thing only we do is that we take a different metal who we want to electroplate, and the anode, suppose, is now replaced with our thing which is being electroplated on the other. So if you want to see an example, you must have seen that some of your jewelries of your mom or your family have a gold covering of it. They say that it is covered with gold. So what do? They take a metal, put it on the cathode, and take the gold and put it on an anode, and they carry out our electrolysis. Now this gold will move from negative potential to this positive potential to this negative potential, and in this way they are covering this metal above which we are electroplating. So we get a gold covered jewelry. So many more cases are there. So suppose we have to protect iron from corrosion. So you know very well that if we expose iron for longer time to air, then it starts rusting. So rusting starts, and slowly this iron decays. So what do? We electroplate with a different metal that is not corroded that much easily. So this is another application of this electrolysis. Now we'll see the most important part of this lecture, that is Faraday's law of electrolysis. So what did Faraday do? So on the basis of his research, he investigated that electrolysis can be quantified. Quantified means we can measure the mass of the substance that is deposited, or we can measure the mass that is depleted on the basis of current we have applied and upon the basis of the nature of the compound we have taken. So he found that electrolysis depends upon the substance, the quantity of substance liberated at electron depends upon three factors. What are those factors? The first one is quantity of current passed. So if you know very well, so more current is passed means more electrolysis is happening. Second, time duration of passing the electrode at uniform rate. So what is the time duration? So for what time it is being passed? First, the quantity of current, it is 1 ampere or 2 ampere or whatever it is, and for how much time this 1 ampere or 2 ampere is implied. Third, and the last one is charge on the ion. So it depends also in the charge. So we'll see something and you'll see that how it is affecting, or the charge is affecting our electrolysis. So this is a Faraday's law. So these two laws, we'll see these two laws. So these two laws are important. So easy questions are asked from these areas. You just have to put the values and get your answer. So be keen to learn these things which give you easily numbers in the exam. So this is our Faraday's law of first law of electrolysis. So what does this law says? It says that mass of any element liberated on an electrode during electrolysis is directly proportional to the quantity of charge, electric charge, which passes through the solution of an electrolyte. Okay, so again, we know that we are slowly introducing this metal on another metal. We are slowly covering it with the help of your current. We are doing an spontaneous reaction. Now, to quantify how much amount or what mass of this element is being liberated on the electrode and electroplated on the other, to do this, to quantify this, the Faraday gave you the law. So the law was that if m is the mass of the substance deposited on the liberator or liberated, and I is the current in our ampere, which is passed for t seconds, then according to law, m is directly proportional to it, where m is the mass of the substance that is deposited or liberated, I is the current, and t is the time for which that current is passed upon. So this is our Faraday's law of first electrolysis. Now what we did is we replace this I, this proportionality constant, and introduced with Z. What is Z? Z is a constant value which is called electrochemical equivalent of the substance. So this is our first law, which says that the mass deposited on our cathode, which is negatively charged, is directly proportional to the current that we are applying and the time for which that current is applied. And upon removing this proportional sign, we have this Z as proportionality constant, and it is called as electrochemical equivalent of that substance. Now, this is our first law. So we'll study more about this Z here, which is called electrochemical equivalent. So what is this Z? Now, if we define the Z, so what do? We know the formula m is equals to Z into IT, where I into T. So one more important formula is that Q is equals to I into T. Okay, where Q is our charge, I is our current, and T is our time. So we know the formula of I is equals to Q by T. So that is to be known. Now what do? We suppose 1 ampere of current we are applying, and that is passed for 1 second. So the product will be 1, which will give you m is equals to Z, right? What does this mean? This means that when 1 ampere of current is passed for 1 second, then the mass of the substance deposited or liberated is equals to the electrochemical equivalent. So it means that when what we are doing, we are taking 1 ampere of current and we are applying to this our electrolysis setup or our electroplating setup, and that is applied for 1 second, and whatever the mass of the substance or the amount of the substance that is liberated is equal to its electrochemical equivalent. Okay, is this clear? So if the formula is molar mass of the metal by charge on cation multiplied by Faraday. Faraday's value is 96500. So what is this Faraday first of all? So for those who don't know, I've told you earlier also. So it is basically the charge. What is 1 Faraday? It is the charge on 1 mole of electron. So how can we calculate it? So very easy to do. What is the charge on 1 electron? Charge of 1 electron, that is 1.6 into 10 to the power minus 19 coulomb. Then what is the charge on 1 mole of electron? So it is simple elementary calculation. So 1 involves 1.6 into 10 to the power minus 19, and we know that 1 mole is equals to 6.022 into 10 to the power 23 entities. So here 10 to the power 26.02 to 10 to the power 23 electron. So it will be 1.6 10 to the power 19 into 0.6.022 into 10 to the power 23. So if you multiply this, you will get something like 96485, which is approximated to 96500 coulomb. So sometimes in exam you will get this value. So if it is mentioned already that you have to take 96485, then you will use this value only, or otherwise if it is not mentioned, you will use this one, which is 96500 coulomb. What is it? It is the charge that is present on 1 mole of an electron. Okay. So this is our formula. So if you want, I will write it into a more clearer manner. Charge on metal multiplied by Faraday. So this is our formula for Z. Okay, is this clear? Yes. Now we'll see the formulation of it. With how we have formulated. So we know that the mass of any substance deposited or freed or at an electrode is precisely proportional to the quantity of electricity carried through the electrolyte according to Faraday's first law. So this is our Faraday's first law, that the mass of substance or that is liberated or freed at an electrode is proportional to the quantity of electricity that we have passed. Now suppose that if W gram of the substance is deposited on Q, when Q coulombs of electricity are passed through it, then W is equals to ZQ, and the electrochemical equivalent of the substance material is Z, where it is the proportionality constant. We have seen it earlier also. So if a current of 1 ampere is passed for t seconds, then we know that Z is equals to M into M. And we also know one more formula, that is charge is equals to current to time. The final formula will be W is equals to Z into Q. Okay, is this clear? So this is the formulation of first law for electrolysis of Faraday. Next is Faraday's second law. So what is this Faraday's second law suggests? So it says that the mass of a substance deposited at any electron passing a certain amount of charge is directly proportional to its this chemical equivalent weight. So it says that if you are, suppose you are the mass of a substance that you are deposited on an electrode is W, then it will be directly proportional to the equivalent chemical equivalent. Okay. Now what do? Suppose we are applying this same current. We are applying the same current on different say substances. Then they will also follow the same law. Okay. That will be W1 proportional to, suppose we have two cases, like W1 proportional to E1. Again, we have W2 proportional to E2. So these are the two weights and we are considering different substances. So we can write here that W1 by W2 is equals to E1 by E2. This clear? So we have just divided these two. So W is the mass of the substance and E is the equivalent weight of the substance. So after dividing, we get it as W1 by W2 is equals to E1 by 2. And the equivalent weight or chemical weight of a substance can be defined as the ratio of its atomic weight and valency. So if you want to calculate this equivalent weight, then it will be atomic weight by valency. So how it is written, that suppose we have a metal like sodium chloride. We are told to calculate it for sodium, the equivalent weight. We know that sodium is 23.5 and its valency is 1. So equivalent weight will be equal to 23.5. Now we have taken suppose a different metal like Na2SO4. So what will the equivalent weight? It will be 23.5 by 2. So you should remember these things minutely because it may result in wrong calculation of your answer during the exam time. Now, let us see an illustration of it, that how we can imagine this Faraday's second law. Okay. For this, we have taken three cases. The first case says that we have sodium plus, which is going to sodium by taking one electron. Second, what we have taken this copper 2 plus ion. Okay, copper 2 plus ion, and it is taking 2 electron and that moving to copper. And in the third electrolysis cell, the reaction is that aluminium 3 plus is going to aluminium. Now first is requiring 1 electron, second is requiring 2 electron, and third is requiring third electron. Now suppose that y moles are electrons are passed through each cell. Then the mass of sodium, aluminum and copper will be what? So if you consider a formula which is like this, which says that W is directly proportional to it. So when supposing that y moles of electrons is passing through this, so if same amount of current is passed through all of this, then same equivalent, not weight, same equivalent of each of this will be formed. So suppose that Na plus chemical equivalence is 23 by 1. So it will be for one mole will be giving one equivalent. So y moles will give 23 into y. Similarly, copper. So it is wrongly written. Sorry, it's wrongly written. Okay. Now here you can see that one aluminium is requiring 3 electrons. Okay, is this clear? So how much electrons will, so y moles will do how much for this? So basically I'm asking that how much gram will be given by this y moles. Now we know that 3 electrons is doing for 1 gram equivalent, 1 equivalent. Okay, so y will give 1 by 3 into y. Okay, this is clear? 1 by 3 into y. And what is the aluminium weight? So aluminium weight is approximately 26 point something. Okay, 26 point something. Okay, so you will calculate it and you will get that it is also giving same electrolyte. Just we are dividing it by the number of electrons. So this is our Faraday's second law. So this was about all of the laws of Faraday's. So first law says that, if you remember it. So this is our first law. It says that M is equals to Z into I into T. That is the mass of the substance that is liberated is equals to Z into I into T. So if we put it in a nutshell, we will write it like this, that mass of a substance liberated is equals to M into Z into I into T, where Z is chemical equivalence, I is the electrical current, T is our time. So how can we calculate Z? It is atomic weight by valency, whatever is the charge on that cation, multiplied by Faraday, that is 96500. I is our current and T is our time. Now this I into T is equals to Q. Q is our charge in coulomb. If I is in ampere and T is in seconds, then in that case we will get our charge in coulomb. This is our first law. And the second law was like this, that weight by Z of 1 is equals to weight of Z by 2 is equals to weight of Z of suppose N. If same current is passed through each of this, Is this clear? So this is our Faraday's law. Each of this. So these are two Faraday's law. So in tomorrow's class, we'll be basically seeing what is batteries. So we'll see what type of batteries we have, primary and secondary. And in the last class, we will be focusing on fuel cell. So fuel cell is very popular nowadays. They are used and in a wide varieties of industrial applications because they have less cost and plus they have low maintenance and they are good for environment also. So the fuel cell is kind of a future. Okay. So this is our class on electrolysis. So with this, I end my lecture.